Hello viewers, today we have a video on multiple integrals. This is a problem that comes straight out of the Stewart Multivariable Calculus book. This comes from chapter 15, section 8, number 35. And the question states, write 5 other iterated integrals that are equal to the given iterated integral. So immediately you might think, well, that's quite a tongue twister, but we'll work through it together. So I'll zoom into the problem, and here's the problem that you'll see in your book. It looks a lot better, a lot nicer. I believe number 35 is actually in bold and in the color red, which indicates there's some additional information that needs to go along with this. So when you look at the integral, we see that this is a triple integral, and this is a function of 3 variables, x, y, and z. And so you have your 3 functions, and they all range dependent on the integral that it refers to. So your inner order of integration is the z variable, and that corresponds to your lower limit of 0 and your upper limit of y. And your x variable corresponds to your lower limit of y and your upper limit of 1. And last but not least, your y variable corresponds to the outer integral, whose lower limit is 0 and upper limit is positive 1. So what we can do to solve this graphically, we can start off by writing all of our variable limits, seeing where they range, and then that will help us to determine what the figure looks like, or at least the domain of this figure. So right now I'll go ahead and write the range of each variable, and that will help us to graph the regions on our three-dimensional coordinate system and figure out exactly what the domain of this figure really truly looks like. So we'll start off with the z variable, which is right over here. And so, as we stated before, z ranges from 0 to y. So I'll say that 0 is less than or equal to z, which is less than or equal to y. And what this says is that z ranges from 0 to positive y. It is greater than or equal to 0, and it is less than or equal to y. And so we'll do much the same for the other 2 variables. So once we look at the x variable, as we've stated before, that the x variable ranges from y to positive 1. And last but not least, we carry on the same process with the y variable, and that ranges from 0 to positive 1. So we can say 0 is less than or equal to y, which is less than or equal to positive 1. So now that we've gotten this information, what we can do is we can find the functions of each variable that will allow us to graph this on a particular plane. So what we can do is we can look at the z variable, and we can create functions using this information that we've derived here. So we can say that z at some point is equal to 0, and z also is equal to y. Equal to y. Hope that's kind of clear. I don't want to add any commas or anything. I don't want to make it any more confusing than it may get. So I'll go ahead and do that for the x variable. We can say x is equal to positive 1. Let's get that 1. And x is equal to y. And so what we're doing, we're not making these things up. We're actually finding the bounds of each variable. Because as you see here, we see that the z ranges from 0 to y. And so what we're doing is we're finding the equations of the upper and lower limits, and that will help us to graph it on a particular plane, like for example the ZX plane. So we're just going to go ahead and use that same concept and go further with the y variable. So from the y variable we can find y is equal to 0 and y is equal to positive 1. Now if you were wondering why I said x is equal to 1 before I said x is equal to y, instead of carrying the same fashion of using the lower limit, making that function, then the upper limit and making that function, there was no particular reason, and that it doesn't really matter which order. We just need our functions, and so that's the most important part here. There is also one thing that is very important to note about this function of three variables. One of the most important things for you to understand about this function of three variables is that the function itself is not a three-dimensional figure. The function itself is actually a four-dimensional figure. Now, it's a four-dimensional figure whose domain is actually a three-dimensional figure. So once we graph the object, we're not graphing necessarily this function. We're graphing the domain of this function here. And so one way to visualize this is think about a traditional three-dimensional object. For example, a box. I'll see if I can create a box. I doubt that will go well, but I'll try. So you've got some type of box in 3 dimensions. So this is our box. Now I want you to imagine shining a light that comes downward onto this object. Let's see if I can get an arrow. So picture the light is coming from this angle, and then a shadow is going to be cast onto some surface. When it's projected onto a surface, like for example this surface here, you're going to get a two-dimensional image, and that image is going to be very much like the domain of a figure. When we were working with double integrals, for example, a double integral is actually a three-dimensional figure whose domain is on a single plane. And so one way to imagine this is imagine a four-dimensional figure. And a four-dimensional figure, imagine casting a shadow on a particular surface. That surface would not be a plane, but instead it would be more than a two-dimensional coordinate system. It would be projected onto a three-dimensional coordinate system, which would give you a three-dimensional object. So when we're talking about this four-dimensional function here of three variables, when we're discussing this, we're actually discussing more so the domain. And when we get that domain, we're going to get a three-dimensional object. So that's something that is really difficult to comprehend, period. The idea of a four-dimensional object. So, but right now we're just primarily concerned about its domain, and its domain is a three-dimensional object that we'll be able to visualize and understand quite well. So we'll just move on. So what I've done here, right, I've already created our three-dimensional coordinate system. We have here our z-axis, our y-axis, and our x-axis. And what I've done on the side is I've actually created the xy plane, which is right over here, and I've also created our zy plane using that coordinate axis, and we also have our zx plane. And so these will help us to visualize the regions that create that three-dimensional domain. And so what we can do is we can start off with the xy plane. I'd say very easily the most familiar plane, and that, in terms of the three-dimensional coordinate system, you can think of the three-dimensional coordinate system itself as being a corner. Like picture a corner of a room, and here you have your little area where all of the walls or planes meet. So you can picture the ZY plane as being one wall, the XZ plane being another wall, and the XY plane, our most familiar plane, as being the floor. So if you're, I'm pretty sure you're in a room, and if you are, chances are there's a corner, whether it be near the ceiling or somewhere on the ground. When you look at it, just take a good look, and you'll notice that there are essentially three planes. There's one wall to your right, one to your left, and the floor itself, and that creates something that you can see here as your three-dimensional coordinate system. So we'll work with the XY plane first. So in terms of the XY plane, the only functions that we will actually be able to see are those functions that are in either the X or Y variables. So if we can identify those functions, which are here, the Y functions and the X functions, those are the functions that we will actually be able to see on the XY plane. So we'll go ahead and plot that and see what types of regions we can create. So let's identify the first equation. We have the first one, which is y is equal to 0. Well, in terms of the XY plane, where is y equal to 0? So if we consider this our little origin right there, a value of 0, where is y equal to 0? Well, y is equal to 0 here, and it's also here, and here, and here, and here, and so on. And so what this means is that y equal to 0 is the equation of the x-axis. And so what we can do is we can just draw a little, or at least thicken in the axis, the x-axis, because that's our indication of the equation y is equal to 0. So I'll just go ahead, denote that there, and I'll see if I can point to it a bit. Okay, so that's our equation of y is equal to 0. Next, we have the equation of y is equal to positive 1. So we'll just go back over to our xy system, and we say, well, where is y equal to 1? Now let's assume that 1 on the x-axis is here. And let's assume 1 on the y-axis is here. Right there. So where is, how do we graph that function? Well, y is equal to 1 is a horizontal line that extends from the y value of positive 1. And so that's our equation of y, y, if I can draw that in, is equal to 1. Yep. And so that's y equals to 1. And so now we have our two functions here, and they are y is equal to 0 and y is equal to positive 1. But this region isn't yet bounded, and so we're not sure exactly where to go yet. So let's look at our equations in x, and we have our first equation in x, which is x is equal to positive 1. If we go back to our xy plane, and we figure out, well, where is x equal to positive 1? And what does that exactly look like? So as we stated before, this point right here would be the x value of positive 1. And so the equation of x is equal to positive 1 would be a vertical line extending from the x value of positive 1. And so now we have some sort of intersection at this point. And so even still, we still don't exactly have much of a bounded region, because we have one function here, we have another function here, another function here, but it's not bounded here. We don't have an equation of x is equal to 0. We haven't gotten that information, so we can't bound the equation, the region as yet, but hopefully with our next function we'll be able to get something more definite. So I'll go ahead and denote that as x is equal to positive 1. So quick review, x equal to positive 1, vertical line extending from the x value of 1. We have y equals to 0, which is the equation of the x-axis, and then we've also plotted y is equal to positive 1, which extends horizontally from the y value of positive 1. So back to our function list, we have in x, we have x is equal to y. Now, you probably already know what x equals to y actually looks like, but in case you haven't seen this or you're not exactly sure what this looks like, it's actually a line that is 45 degrees from the positive x-axis in this case. So we're talking a line that goes straight through. Now, if you want to visualize this even more, think about what happens as we increment our values for x or our values for y. So the equation of x is equal to y, let's assume x is positive 1. So if we assume x is positive 1, which is located here, x is equal to y says that x must equal y. So if x is positive 1, so must y, and so we have a point here. And if x is 0, so must y, and so that must be here. And so when you do this significantly with a ton of numbers, you'll actually find that it's a 45-degree line in this first quadrant, and it extends onward. And so now we've actually found a bounded region. But before we go to that, I'll go ahead and denote this as x is equal to y. It's also x is equal to y is also y is equal to x. All the same in this particular case. So now we have a region. It's bounded by the equation x is equal to y is equal to 1, x is equal to 1, and y is equal to 0. So what I'll do is I'll go ahead and shade in this region because this is what we're primarily concerned about. So now we're going to move on to the ZY plane. And so what we do is we go back to our list of functions that we created earlier, and we only focus on those that are of the variable z and of the variable y. So I'll just go ahead and start off with the z variable first, and I'll say, okay, the first equation is z is equal to 0. Now, when we look at our zy plane and we consider this point here as the origin, where is z equal to 0? And z is equal to 0 is very much comparable to the equation y is equal to 0 on the xy plane. And so z is equal to 0 would be this horizontal line here, which is actually the equation in this plane of the y axis. So I'll go ahead indicate that here by darkening it in. Well, not necessarily darkening in, but I'd say thickening. And so we'll say that is z is equal to 0. Once again, try to point at it, make that clear. And so now we'll move on to our other equation. And so our other equation is z is equal to y. Now, again, very much comparable to something we did in the xy plane. And in the xy plane, we had a function of x is equal to y. And so now we have a case where our function is z is equal to y. And so on the zy axis, it looks very much the same. So we have a 45-degree line from the positive y axis. And so that is what our function graph would actually look like. And so I'll denote that here, z is equal to positive y. So we have two functions graphed, and it looks like we're getting somewhere, but we have to bound this in order to really take seriously this region. So we'll keep going. We've already used our two equations in terms of z, and so now we'll go and look at our equations in y and see what we can find there. So here in y we have y is equal to 0, and y is equal to positive 1. So we go back to our zy axis and we say, well, where is y equal to 0? So y is equal to 0 all along the z-axis. So I'll go ahead and darken that in all the way up. And so this would be our function y is equal to 0. Try to point at that as well. So here we have three functions. We have z is equal to 0, which is here. Z is equal to y. And we have y is equal to 0. So you're probably saying, well, I'm not even sure with the remaining equation if we'd even find a boundary region. Well, let's go ahead and find out and see if that is or isn't the case. So last but not least, we have y is equal to positive 1. So we go back down to our zy plane, and we say, if that this point here is a value of y is equal to 1, and the equation y is equal to 1 would be a vertical line extending upward from the y value of positive 1. And so now we have an actual bounded region. It's bounded by z is equal to y, z is equal to 0, and y is equal to 1. So I'll go ahead and indicate that. Let's see where. I'll probably put that here. Y is equal to positive 1. Point at that. So there you go. Now you're probably saying, well, whatever happened to this function here, y is equal to 0? Well, when we actually graph the domain of this figure, you'll see where this comes in. But for now, we're primarily concerned with the bounded region that we found from the equations y is equal to 0, y is equal to 1, and z is equal to 0. So I'll go ahead and shade in the bounded region right here. Let's see. Okay, that's pretty good. And so if you look at these two regions from the xy plane and the zy plane, you actually notice they look, practically identical. And what you'll realize is when we move on to our three-dimensional coordinate system, you'll notice that our xy plane will be a triangle on the floor of the system, and our zy region would be a triangle on the zy plane. So you'll have one region on the floor, one on the right hand side wall, and what you need to realize is that each one of these equations that we've plotted in one variable is actually an entire plane. And so the intersection of these planes will actually create our three-dimensional image that will help us to find the other iterated integrals that are equal to our initial iterated integral. So right now we can begin our visualization process where we try to identify what exactly the domain of this four-dimensional figure would actually look like. So we start off with our regions in 2 dimensions, and we extend those regions merely because every equation that we've graphed is a full plane. And so when we extend those regions and we find this intersection, we should certainly be able to find what our image looks like. And so we'll go ahead, zoom into our three-dimensional coordinate system, and we look at the floor of the system, our xy plane. And our xy plane, we have it bounded by the equations x is equal to positive 1. So we'll start off with x is equal to positive 1. So this is the positive x-axis, positive y-axis, and positive z-axis. And so x is equal to positive 1, let's assume is right about here. And so that equation, x is equal to positive 1, would extend upward like so. And then we have our equation x is equal to y, which starts out at the origin and meets it at a point of x is equal to 1, and also that bounded equation, which is y is equal to positive 1 here. And so it's actually bounded right there, assuming that this point is y is equal to positive 1. And so this is the region that we are working with on the floor. And so this region can be extended up the z-axis and below the z-axis. It's very hard to visualize this, but it'll get simpler as we continue with the process. And so we'll move on to our zy axis. And when we look at our zy plane, on the zy plane we have this triangular region. Now fortunately, because of the nature of this particular three-dimensional coordinate system, we don't have to actually flip the triangle. It's very much graphed the way it would be on this right-hand wall. And so we can go ahead and graph the function of y is equal to positive 1. And so y is equal to positive 1, assuming, let's assume that point is y is equal to positive 1. It would extend upward like so. And then we have our equation z is equal to y, which would come from the origin, 45-degree line from the positive y-axis, and they would connect like so. And so now we have our region here and here. Now again, like I've said before, this region extends outward like so, outward in both directions, because these are all planes that we're really talking about, and this region extends upward and downward. And so what you'll notice is that when this region extends toward the left and this region extends upward, there's going to be some intersection about here. And that intersection is exactly what we need to figure out what the domain of this four-dimensional image actually looks like. So I'll see how this goes in terms of showing you exactly how these planes extend. So you have, let's see if I can get a small tip. Okay, so this extends outward like so, this extends outward like so, and this extends up, and this goes up. So now you're probably seriously saying, what mess is this? But as I said before, it'll get easier once we look at it in a much better way. So let's create another three-dimensional coordinate system. We have our y-axis, x-axis, z-axis. So as we had before, we had a region that looked very much like this. We had another region on the wall. But when that region projects outward and meets the region here, which is a series of three planes that extend upward, when they all meet, you're going to get an image that looks very much like this. See if I can get this. So this is a very, very rough image of exactly what our domain would look like. So I'm not sure if you can see exactly what this looks like, but this area here that's indicated by this dashed line, that dashed line is actually the bottom portion of this figure. And so remember our region that we found on the XY plane, which is a triangle, and we had our triangle back up here. We had our equation of x is equal to positive 1 and x is equal to y, and last but not least, our equation y is equal to 0. And so that equation is this triangle at the bottom of this figure. And so what we did to create this image is we took our image that we created, our region, on the ZY plane, which was a triangle, and that triangle would be located right here, and it would look very much like this. And so what we did is we projected that outward onto this region here, and what you'd find is you'd find a very slanted front region here that corresponds to that initial slant of this right triangle that we created on the ZY plane. So it would be slanted on the top, it would have a straight end near the back, it would have a flat plane right here, and the bottom base of this is a triangle. And so this is what our figure would look like. And so now that we've created our figure, we would actually be able to identify the equations of each surface of this figure, and that'll help us to find the iterated integrals. So right now I've realized that this is probably a very poor image. Hopefully this is slightly better. This is actually written on paper, and once we zoom into this, what we can do is we can actually identify the planes and the equations of each of the planes. So right here I've indicated x is equal to positive 1 as being this face that's closest to our viewing angle. And so you're probably wondering, well, where exactly did that come from, and how exactly did I know that the equation of this plane would be x is equal to positive 1? Well, if we go back to our xy region is located here, and our xy region has an equation of x is equal to positive 1. Now remember that this entire xy region is on the floor of our three-dimensional coordinate system, and so the equation x is equal to 1 is a plane that extends upward. And so when we compare that to our image here, our xy plane is right here, and so our function of x is equal to 1 would be here, and that plane extends upward and downward. And so that's why and how we know that the equation of this face is x is equal to positive 1. So I've also denoted an equation of z is equal to 0, and this arrow actually points to the bottom portion of this figure that sits on the xy plane. So you're probably wondering, well, how on earth did I get the equation of z equals 0 to be the bottom portion of this? Well, when you look at the three-dimensional coordinate system, the equation for the xy plane itself is actually z is equal to 0. And so that's how I found this here. So when z is equal to 0, which is this point, x and y are unbounded in all directions. So it extends outward in every single direction. And so that is the floor or the base of this figure. And so that's how I found the equation of z is equal to 0. And so here on the right hand side of this figure, we have this wall here, and that wall, I've denoted that as being the equation y is equal to y. So you're probably wondering, well, how exactly is the equation to this wall equal to this function y is equal to y? Well, if we go back to our function, to our region in the xy plane, we have our function here, which is y is equal to x, or x is equal to y. And so we understand that that's a 45-degree line from the positive x-axis. And so when we compare that with our three-dimensional coordinate system, that same 45-degree line from the positive x-axis is this dotted line here, which is below the figure. And this line is actually projected upward, and it creates this surface at the top. And that surface, this entire plane itself, would be the equation of this line in the xy plane. And so that's why I've denoted this face as being the plane equation y is equal to y. So right now we've already identified the plane that covers this surface here, which is x is equal to 1, the plane that covers the right-hand surface of this figure, which is y is equal to x, or x is equal to y. But we have to identify what is this slanted area here. Okay, what is the slanted area? How is it formed? Where does it come from? All of these questions we can answer. So remember back to our ZY plane. Our ZY plane is here. And the region that we found is this triangular region that starts here at the origin of this ZY plane, and we get this triangular region. When we compare this to the three-dimensional coordinate system, you'd find a triangular region that starts here at the origin, moves up like so, and down like so. And I think you can even see little eraser marks of when I drew this to actually figure out what the image would look like on this side of the figure. So when we have this triangular, right triangular region here, the slope of this 45-degree line, which we identified earlier to be the equation z is equal to y, that's where that comes from. So we understand that this line here would be the equation z is equal to y. And that plane extends outward. That extends outward all the way, and it cuts the figure at an angle, at that same 45-degree angle all the way through. And so what we can say is that at every single point on the top of this figure, we understand that that is the plane z is equal to y. And so that's why and how I've denoted this top surface to be the equation z is equal to y. So right now we actually have all of the information that is required for us to figure out graphically what the 5 other iterated integrals equal to the given iterated integral would be. But I also included, you're probably wondering, well, I've seen what the image would look like from the z-y axis. I've seen what it would look like looking top down onto the xy axes. Well, what does it look like from the zx plane? Well, I'll show you briefly exactly what that looks like. So on the zx plane, we've already created our figure with all of these equations, and it's even unnecessary, but it's also pretty nice to view it from the zx plane. So I'll go ahead and graph our function in x, which is x is equal to 1. And so if we assume this is the point x is equal to 1, x is equal to 1 would extend upward, vertical line, at the point x is equal to 1. Now when we look at our equations in z, we notice that there is z is equal to 0, which we can easily graph, and z equal to 0, assuming that's the origin, would be the equation of the x-axis in this particular case. And so I'll go ahead and denote this really quickly. X is equal to 1 and z is equal to 0. Arrow. There you go. And so if we look at the other equations in z, we have z is equal to y. Well, z is equal to y can't actually be viewed from the zx axis. So you're probably wondering, well, what can we put to actually bound this region and figure out what it would look like? Well, it takes a bit of projection. When we look at the three-dimensional figure based on the regions that we found previously, and we try to take a look, coming in, looking toward the figure from this angle. When we look at the figure, we'll be able to identify the equation of x is equal to 1. But there's also this slant line here, this slanted line right here. And the equation that corresponds to is y is equal to x. And when y is equal to x is bounded at any point, if we were to project this line onto the zx plane, the actual translation of that would be an equation that would be z is equal to x. So it would actually look like this. So that's what happens when you actually project that line over. So it's something really cool to think about, to look at and investigate further. But in terms of this problem, that's a bit of information that we don't actually need. We have everything on the figure already labeled, and this is sufficient enough for us to find the 5 other iterated integrals. So now if we go back to our original question, the question states that we ought to find the other 5 iterated integrals equal to our given iterated integral, which is right here. And so the first thing to know is that there are 6 orders of integrals for triple integrals. So there are 6 total orders. So that's every single unique combination of our dz, dx, and dy variables. So what's important is that they've already given us a head start. They've already given us flat out one of the iterated integrals. And so what's important is to identify what this exactly means in terms of our figure here. So one thing to note is that your inner variable can at most have 2 variable limits. Your middle integral can have at most 1 variable limit, and your outer integral must have 2 definite limits. And that's in order to actually find a volume. So in terms of our 3D image, which we found here, our inner order, or our inner variable for our triple integral is z. And they have here z is equal to 0 and z is equal to y. So how did they figure this out, and how exactly does this work? Well, for your inner integral, what you do is you identify what your inner integral is in terms of. So whatever that inner integral is in terms of, and for that variable. So in this case, our inner integral is in terms of the z variable. And so what you do is you identify the z-axis on your three-dimensional coordinate system, and you create a parallel line that is parallel to your z-axis, and you run that straight through your image, your figure. And so if I were to do that now, I'd zoom in a bit, and what we'll do is we'll create a parallel line that is parallel to the z-axis running through the figure. And so I'd go right up to the figure, and I'd enter the figure, at some point, and then I'd go through the figure, and then I'd come right out of the figure. So you go through the base of the figure and then out through the slanted top of the figure here. And so where these limits come from, it's simply the equations of the planes that this is running through in terms of z. So if we look at our figure, where does it enter? By the way, when you draw your parallel line parallel to the given axis of a particular variable, you draw it from the negative portion of that axis to the positive. So negative to the positive portion. So when we look at our lower limit, what is the equation of this plane? Well, we've already identified that in terms of our z variable as z is equal to 0, which is right over here. And we know this is true, as we've stated before, because we understand that this is the z-axis. We understand that the equation z is equal to 0 is the entire xy plane, and we understand that the base of this figure is the xy plane. And so thus, the entrance point would be of the equation z is equal to 0. And so that corresponds exactly with what they have here. They have their inner order, which is a lower limit of z is equal to 0, and then it has an upper limit of z is equal to y. So where does that come from? We go back to our image and we say, well, where exactly does this exit the figure? It exits the figure at this slanted surface, and we've identified that as z is equal to y. And so we go back down here, and that corresponds exactly with what they have here. Z is equal to y. So that's great. So that's how you figure out your inner integral limits. When you look at your two outer limits, your two outer integrals and their limits, what you do is you project the image onto the plane of the remaining two variables. So in this particular case, we would project the figure, the domain of this figure, we'd project that onto the xy plane. And so when we do this, you will find, so this is our projection of our figure onto the xy plane, and when you do this, we get very much the region that we obtained earlier. And that same region is what they've used to find these limits. So back to double integrals, you use the same double integral techniques to figure out what the limits would be. So you understand that your outer variable and its integral must be of definite values. So what they've done here is they've looked at the x variable, and they say, based on this projection, they say, okay, well, how does x range? What does it range from? And so what they did is they created some type of line that they passed straight through the figure. I like to use little rectangles because it's very similar to the techniques used in Calculus 2. And so we read this and from left to right, very much the way you would read any piece of text in English generally. So what is the equation of the line that this rectangle hits on the left? And that we identified earlier as the equation x is equal to y. So in terms of x, that would be y. So we begin at y. So when we look at the second integral, we notice that the lower limit is y. And then we look to the right side of this rectangle, and we look at it and we say, well, what is the equation of this function that it's touching? And we notice that this, as we've stated earlier, is the function x is equal to positive 1. And since that is already a function in terms of x, we can just use our upper limit as positive 1. And see, that corresponds exactly with the upper limit of the second integral. And based on your techniques from double integration, you understand that your outer variable's integral must have definite limits. So your y variable, it begins at a value of 0, and then it extends all the way up to a value of positive 1. And so that corresponds directly with the outer integral's limits, which begin at 0 and end at positive 1. So this is what they've done. This is exactly what they've done. And so all we have to do is figure out the other order of integration, keeping z exactly the same, projecting it onto the exact same plane, which is the xy plane, and just using, instead of a horizontal rectangle, we'll use a vertical rectangle, and then switch around dx and dy. So it's very much like a puzzle, you can think of it. And so what we can do is we can go ahead and write our first three integrals, our function here, f of x, y, and z. And dz is staying the same. We have yet to change our inner integrals axis. We've yet to change that. Right now we're trying to find the other 5, and in order to do that we have to switch it around quite a bit. So this will be dz So as I've stated before, your limits for your inner variable will remain exactly the same. So that will range from 0 to y. So that will stay exactly the same. 0, y. And so we've switched around dy and dx. And so on our xy plane, instead of using horizontal rectangles, we can use vertical rectangles. So we'll do this. Let's see if I can get that. Rectangle. So once we've gotten that down pat and we've created our vertical rectangle, and we understand first and foremost that our outer variable corresponds to our first integral, and those limits must be definite. So in terms of x, when we look at our xy plane, how does x range? Definitely, it ranges from 0 all the way to positive 1. 0 to positive 1. And so we can go ahead and put that there. 0, whoops, I'm in another color. Let's see if I can get out of this. So that's 0 to positive 1. And then we look at our projection on the xy plane, and we use that yellowish vertical rectangle in order to figure out what our limits would be in terms of the y variable. So how does y range? We go from this function here, which is actually the x-axis, whose function in terms of y is equal to 0, and it goes from y is equal to 0 all the way to the top of this line here, which we identified earlier as y is equal to x. So in terms of y would range from 0 to x. And so that's what we can put for our second integral here. So once we've done this, it's important to understand that we've fully exhausted the orders of integration while keeping the inner integral as the z variable. So once we have dz corresponding to our inner integral, there's only two orders that we can flip these two around. It's either dx dy or dy dx. And so we've already exhausted that. And so in order to find the remaining iterated integrals, we have to actually change our inner integral and what variable that corresponds to. So you can do that arbitrarily. For me, I will go ahead and pick the x variable to be our inner order. So f of x, y, z, and here I'll put dx, dy, dz. So based on the order of integration that I've picked for us to solve next, we understand that our inner integral corresponds to the x variable. So what that means is that there's going to be a line that passes through our figure that is parallel to the x-axis, and that'll help us to determine the variable limits for the inner integral. So we go back to our figure and we look at the x-axis, which is here. This is the positive x-axis, this is the negative x-axis. I'll pick another color for our line, and what we'll do is we'll take a line and it passes through right here, and then it pierces the figure, pierces it right there, and it comes all the way through. Whoops, I should have did a dashed line there. Let's see if I can do that. So that looks a bit better. So we have a line, it starts from the negative x-axis, it runs through our figure, and the first thing it hits is this side right here, this surface. And then it runs through our figure and then out of this surface here, and it extends onward. And so what we do is we figure out, well, where does it enter our figure? And it enters our figure right here at this plane, this surface right here. So what on earth is the equation of that plane in terms of x? Well, we've identified that plane to be of the function z is equal to x. So in terms of x, the limit, the lower limit of that integral would be y, and then it extends all the way through, and then it comes out right here at this surface, and we understand that surface to be of the equation x is equal to 1. So what it would do is it would come through, the lower limit of that integral would be y, and then it would come out to x is equal to positive 1. So x is equal to y here, and x is equal to positive 1 here. So back to our order, our inner variable, we'll go ahead and say x is equal to y here, and 1 up there. And so we're almost finished. We just have to project our image onto a particular plane. And because our remaining variables are z and y, we simply project our figure here. We project that onto the zy plane, and that will help us to figure out the remaining limits for these variables and their integrals. So once we look at our region that is projected onto the zy plane, we will get this triangular region here, and the variable of our outer integral is z. And so what that means is that in terms of z, we must have definite values. And so we look at z and we say, for this particular region, how does z range? So we go down and we look a little bit closer. We say, well, if we draw, for example, a horizontal rectangle, we can actually see how our y variable ranges. So we look at y, we understand that y is our second integral that corresponds to our second integral. And so we go ahead and we say, well, how does y range? Y ranges from left to right. So on the left, this rectangle touches this function here. And so Here, y is equal to z. And on the right side, y is equal to positive 1. That's the equation of this vertical line here. So y ranges from z to positive 1. So we can go ahead and put that right over here. We can go z to positive 1. And then, as I was stating before, we understand that our z variable must have definite limits for its integral. So we look at z, how does it range? Z ranges from z is equal to 0, which is the equation on this coordinate axis for the y-axis. So that will be z is equal to 0 all the way up to z is equal to positive 1. How do I know that this intersection point is z is equal to positive 1? If you look at this line here has an equation of y is equal to positive 1. This line here has an equation of z is equal to y. So if y is equal to 1, so must z. So therefore, this point here has a z value of positive 1. So z ranges from 0 to positive 1. Go down here, and we say z ranges from 0 to positive 1.